Namaskaram. Today we are going to discuss about double integration. Before moving to double integration, first we are going to discuss, first we are going to analyze what is single integral, especially the relation between definite integral and infinite sum. That means in this session, first we are going to interpret a definite integral as a infinite sum. We know that a definite integral a to b f of x dx, represents area between the function f of x and x-axis from a to b. That is, okay, so area between, this is our function f of x, area between function and x-axis from a to b. Okay, next we are going to evaluate this area. Area is equivalent to this definite integral. So next we are going to evaluate this area using an infinite series. Okay, so how to interpret or how to evaluate this area in another way. For example, we subdivide this interval AB as n intervals. Denote a naught as x naught, this point is x1, etc. This point is xn. So xn is b and x naught is a. So we have n subintervals, and we denote the length of each subinterval. The length of first subinterval as delta x1, and delta x2 is the second length of second subinterval, etc. The length of last subinterval is delta xn. Okay, so delta x1 is this length. This length is delta x1, and this length is delta x2, like that. Okay, we have n subintervals. Then how to estimate this area? For example, we choose a point, we choose an arbitrary point from the first interval. Let it be some x1 star. So x1 star is any arbitrary point from the interval in the first subinterval. Similarly, we choose x2 star from the second subinterval, etc. We choose xn star from the nth subinterval. Okay, then you think about the function value at this point. Then you imagine the function value at this point. Here the function value means this height. This height gives the function value at this point. Okay, then my question, what is the quantity f of x1 star into delta x1? What about this quantity? Here f of x1 star is this height, and delta x1 means this length. So this length into this height, that gives the area of this rectangular region. Okay, then our aim is to evaluate this red area. Then what about this infinite sum? Then my question, what about this infinite sum? F of x1 star into delta x1 plus etc. plus f of xn star into delta xn. That is, in symbolically, sigma k is equal to 1 to n f of xk star into delta xk. What about this quantity? This rectangle, or similarly the next rectangle like this, and etc. like that, etc. The last rectangle is somewhere here like this. Okay, what about the sum of areas of all these rectangles? The sum of all these rectangles is approximately the area of this red region, the area between this curve and x-axis from a to b. Okay, so that's why using this notation we can approximate this area using this sum, this finite sum. Then how to improve this finite sum as an area? Okay, if n is large, or if size of this rectangle is small, if the size of this rectangle is small, then automatically error is minimum. Now it is clear that there is an error. Okay, a small error in first approximation. Okay, you can reduce this error if we reduce the size of each interval. It is possible when n is very large. If you increase the number of subintervals, then automatically the size of each interval is very small, then automatically it reduces the error. So as a limit, we can find this red area using limit n tends to infinity sigma k is equal to 1 to n f of xk star delta xk. Okay, so we know that this integral also area, this infinite sum also area, gives the same area. So we can equate these two. That's one interpretation of this definite integral as a infinite sum. Okay. So we can conclude that limit n tends to infinity, sigma k is equal to 1 to n, f of x k star delta x k is equal to integral a to b f of x dx. Okay, so we can represent these type of infinite sum as using this integral. You got it? So using this notation, we are trying to generalize double integral using this type of. That means double integral is a generalization of this type of infinite sum. Okay, so first of all we are going to introduce this type of an infinite sum, then we denote that infinite sum as a double integral similar to this single integral. Okay, so in this representation here this f of xk star become f of x under the integral sign, and this delta xk is become dx. That's a idea. Okay, so next we are going to evaluate the volume of a surface is the volume between a surface is equal to fxy and the region R. Then how to find this volume as a infinite sum? How to find the volume as a infinite sum? The technique is similar to our one-dimensional case. First of all, we are going to divide this region R as small rectangles using lines parallel to coordinate axis. Okay, and we consider only the rectangle is completely inside R. We consider the rectangles completely inside R. Okay, and we throw out the rectangles on the boundary. You got it? That means we exclude all sub-rectangles that contain any point outside R. Okay, suppose there are n such rectangles are there. Suppose the region R contains n such rectangles. And similar to one dimension case, here we assume that the area of the kth subrectangle is delta ak. That means let it be this one is first rectangle, this is second rectangle, this is third rectangle, etc. up to we have n rectangles are there. And we assume that delta a1 is the area, this area is delta x1. You got it? And delta a2 is the area of the second rectangle, like that. Okay. Then how to approximate this volume between this surface and the region R? As similar to one dimension case, we find the volume of this type of rectangular solids. As similar to one dimension case, here we try to estimate this volume using sum of n such parallelepipeds. Then what is the volume of this parallelepiped? How to approximate this volume? To approximate this volume, the technique is like this. Technique is similar to our one-dimensional case. Choose an arbitrary point from n such rectangles. In the case of one-dimensional case, we choose a point x1 star, x2 star from each subinterval. Here we choose an arbitrary point from each rectangles, okay, denoted by xk star, yk star. Then how to find the volume of this parallelepiped? Here the volume of this parallelepiped is given this formula. We know that delta ak is the area of this base rectangle, and what about this height? Height is given by f of xk star yk star. So the product of this height into base area, that gives the volume of this yellow parallelepiped. Okay, we have to find the volume of this entire region. Then how to approximate this volume? You take the sum of all such parallelepipeds. You got it? So the volume of this region, the volume between the surface z is equal to fxy and the region R is approximately sigma k is equal to 1 to n f of xk star yk star delta ak. You got it? Because this is equivalent to f of x1 star y1 star into delta a1 plus etc. plus last nth term, and this means the volume corresponding to the first rectangle, then volume corresponds second rectangle, etc. like that. So this volume is approximately, so this sum is approximately equal to the volume because we throw out these boundary non-rectangular shapes. Then how to improve this sum? We can improve the sum by taking small rectangle. That means if n is very large, automatically the size of each rectangular shape, each rectangle is very small. Okay, so the volume of this region is exactly equal to limit n tends to infinity sigma k is equal to 1 to n f of x k star y k star delta a k. You got it? So this is the limit form of volume between the surface z is equal to fxy and the region R. Okay, in the case of single integral, the limit n tends to infinity sigma k is equal to 1 to n f of xk star delta xk is denoted, or which is equal to integral a to b f of x dx. So this is a compact notation of this complicated infinite sum. Okay, analogous to this representation, what is the integral representation of this infinite sum? This is also an infinite sum. Only difference, instead of a single variable function, here we use double variable function. That's all. Okay, so what is the analogous notation? Okay, in the case of single variable calculus, we integrate in the interval AB. Integrate in the interval AB. Here we have to integrate over the region R. You got it? That is a change. Okay, instead of length, instead of the length delta xk, here we use areal element delta ak's. So what is the integral representation of this infinite sum? Yes, this is exactly equal to, instead of instead of single integral, we use the double integral. Okay, here we integrate from a to b. That is our region of integration. Here the region of integration is a to b. So here the region of integration is R. R is this region. This entire region is our R, the base region. Okay, and what about the function? Here f of xk star become f of x. So here f of xk star yk star. What happened? So this become f of xy. You got it? And what about delta ak? Here delta xk become dx. So what about delta ak? That become dA. Okay, so this is the integral notation of this infinite sum. So analogous to one-dimensional calculus, one-dimensional integration, we can represent this infinite sum, limit n tends to infinity sigma k is equal to 1 to n f of xk star yk star delta ak is denoted by double integral over R f of xy dA. Okay, this is only notation. This is the actual value. This is only notation, as similar to one-dimensional calculus, one-dimensional integration. Okay, then there is a natural question: how to evaluate this double integral? Okay, presently we can evaluate this double integral using this sum, but this sum is not easy to evaluate. This is almost impossible to evaluate using this formula. Okay, so we have to find some simple formulas for evaluating this double integral. In next session, we will evaluate this double integral using iterative integrals. That means multiple single integrals. We can evaluate this double integral using multiple single integrals. Okay. That means we can evaluate this double integral using our single integration. Single integration 2 times. We will see that in coming sessions, coming slides. Okay. First, so before moving to that concept, first we have to evaluate a double integration like this. This is called iterative integrations. First we integrate with respect to y. At that time we treat x as a constant. Then we integrate with respect to x. Okay. So resultant is integrated with respect to x. So how to integrate this expression? This is very easy, because first you integrate with respect to y, treating x as a constant. So this becomes integral 1 to 3. What about the integral of 40 with respect to y? That is 40y minus 2x is a constant, because integration is with respect to y. So we can treat 2x as a constant, and y become y square by 2 and 2 to 4 dx. Okay, you can cancel these two and substitute an upper limit and lower limit. Then this become integral 1 to 3, and this expression after simplification 80 minus 12x dx. Again you can integrate this 80 minus 12x with respect to x. So this become 80x minus 12x square by 2 and 1 to 3. Upon simplification this become 112. Okay, so the answer of this double integration is 112. Okay, so this is called an iterative integration. First we integrate with respect to y, then we integrate with respect to x. These type of integrals are called iterative integrations. Okay, so similarly we have one more problem. The same question, only thing is we change the order of integration. First we integrate with respect to x, then with respect to y. So the limit of x is 1 to 3 and limit of y is 2 to 4. Okay, and what about this integration? First we integrate with respect to x, then this become 40x minus 2x square by 2 into y, and upper limit is 3 and lower limit is 1. So after simplification this become integral 2 to 4, and the inside function is 80 minus 8y, 80 minus 8y dy. Okay, again you can integrate this with respect to y. So what happened? So inside become 80y minus 8y square by 2, and upper limit is 4 and lower limit is 2. Upon simplification this become again 112. Yes, answer is 112. This is not a coincidence. There is a reason behind this. Okay, we are going to analyze this closely. Why both gives the same answer? Okay, first we analyze our first example. So we consider the solid bounded by z is equal to 40 minus 2xy. Z is equal to 40 minus 2xy is a plane like this. It's a slanted thing. Okay, so this is the shape of z is equal to 40 minus 2xy. Whatever be, anyway, first we integrate this expression with respect to y. Then what is the geometry of this integration? We know that when we integrate with respect to y, we are treating x as a constant. Suppose x is somewhere here. We know that x is always between 1 and 3. Okay, first of all we assume that x is somewhere here. So we are fixing x. Okay, we fix x. So only moving thing is y. Y is moving. You got it? X is fixed, y is moving. So we integrate along y. So here we integrate integral 2 to 4 40 minus 2xy with respect to y. So that means this is a function of y. Then what is the integral of function of y? It is like a single definite integral. We know that single definite integral gives area. We can interpret single definite integral as an area. The only thing is x is a constant. Now x is a constant. We don't know what is the value of x. X is between 1 and 3. Suppose we fix x is here as a constant, then this gives area. Area between this line segment and this line segment. That means this integral gives area of this yellow region. You got it? Because when x is a constant, 40 minus 2xy is this one. This is 40 minus 2xy. Okay, this graph is 40 minus 2xy, isn't it? Z is equal to 40 minus 2xy. When treating x as a constant gives this line segment along this surface. Okay, so integration gives the area between this line segment and x. Instead of x-axis, this line segment parallel to y-axis. Okay, and again, now next we are going to evaluate integral 1 to 3. Let it be some areal element. Actually this yellow region is an areal element. Okay, next we are going to integrate this areal element with respect to x. That means what? We are going to sum up all such areas. Suppose x is here, then we get this yellow region. Suppose x is somewhere here, then we get area like this. You got it? We get an area like this. Suppose x is here, then we get a big area like this. You got it? We integrate with respect to y at this x, then we get area like this. And you imagine integration of all such areas, that is integral 1 to 3 ax dx. What about summation of areas? The summation of areas along this direction gives our volume of the solid. Okay, similarly you can interpret other integration, our second problem. This is our second problem. In this second problem, it is clear that okay, we have seen that 1 to 3 40 minus 2xy dx is the first integration is 80 minus 8y. And what is 80 minus 8y? In the case of first integration, we are treating y as a constant. That means we fix y somewhere here. Okay, we fix y somewhere here means only x is moving. So the graph of the surface along this fixed y is like this. You got it? Then we integrate this function. Now we can treat this is some function of x because we're treating y as a constant. Then integral 1 to 3 g of x dx. This is the curve g of x, isn't it? Then what about integral 1 to 3 g of x dx? That gives area under this curve. Okay, so this yellow region is this integration. This integration gives this yellow region. You got it? Its value is 80 minus 8y. So 80 minus 8y is the value of this blue area. It depends y. Suppose y is here, then it gives area is like this. You got it? So naturally this area depends y. Okay, next we are going to integrate this areal element with respect to y. That means we are going to sum up all such areas in the y direction. That gives the volume of the same element, same solid. That's why both integration gives same 112, same volume. Okay. Okay, you got the idea. So in next session, we will see what is the relation between this double integral. This is only a notation of this infinite sum. In next session, we will see what is the relation between this double integral and the relation between iterative integrals like this. They are called iterative integrals, either dx, dy or dy dx, whatever inside some function is there. And in this session, we will see what is the relation between this double integral and these type of iterative integrals. Okay. Okay, thank you.